That's a big 5.7 metre tall satellite. It's huge, and it's a telescope. It's designed to look down at the Earth, and it cost about $307 million to build. So when you put $307 million into something, you probably want to make it last a while. And that doesn't even include the cost of getting it into space. And it takes lots of photos each day, and the pictures are so good that you can count the number of cars in car parks. And so each pixel from one of the photos from Worldview 3 is actually about 30 centimetres. So from space you can see something that's that big. And so, you know, that's pretty good, and obviously the people that operate that, they sell those images. Landsat 8, you know, it's a bit smaller on the scale there, only weighs 2 tonne. It takes a lot of different photos of the Earth at different wavelengths, so it's used for things like precision agriculture and monitoring crops and forests and things like that. Moving down in the size, we've got Skysat. So Skysats are from a company called Skybox, who was actually acquired by Google, and they're about the size of a dishwasher. But they can actually take videos, real-time videos from space. And one of the first videos that they took was actually of Perth, and you could see cars driving down the road from space. So I thought that's pretty amazing for a dishwasher in space. And then you get a bit smaller, and then you've got Planet Labs, a US-based company. They make these 3-unit Cubesats, so 30 centimetres by 10 by 10 centimetres. So they're much smaller. But each pixel from one of their images covers about 3 to 5 metres. So you're not going to be able to see people, you're not going to be able to identify people, but you can get a pretty good idea about what's going on the Earth below. But the price of all these satellites, not only are they decreasing in size, they're decreasing in cost. And so if you see my satellite down the end there, it's probably that one white pixel there. That's about the size of OzCube in comparison to these other satellites. So what is OzCube-1? It's a pocket cube satellite. So most people have never seen a satellite this small before. It's a new form factor that's only 5 by 5 by 5 centimetres. So it's 1/8 the size of a Cubesat. So a Cubesat is what a lot of universities around the world build, and they're 10 centimetre cubes. So this is even smaller. But inside it's made up just like a bigger satellite. It has discrete subsystems that perform all the satellite functions. And so here's sort of a photo of the inside of OzCube-1. It has the same building blocks as the bigger one, so it has a command and data handling module. So that's like the brains, the computer of the satellite. And that talks to a radio transceiver. So you need to be able to communicate with the satellite to get information to and from the satellite. It has a power supply, so it needs to get power from its solar cells, and it converts that into something useful that the satellite can manage. And then it needs to transfer that power to a payload. So in the case of OzCube-1, the payload is a camera. So just like those satellites you saw on the slide before, mine's taking photos from space, but it's just a lot smaller. And what does OzCube-1 do? So as I said, it has a camera, so its mission is to take photos of Australia. And because of the nature of the satellite and the way that it's configured, it'll actually take photos of southern hemisphere targets, but it's going to take photos of Australia, but it's going to be able to transmit them worldwide. And anyone who's got some fairly low-cost hardware is actually going to be able to receive these images. So the images are going to be shared by everyone worldwide, and they'll see that there are pictures of Australia from an Australian-built satellite. And that's where the secondary mission of it is to come in and inspire other people to say, well, here's a guy building a satellite in a garage, and it can take photos from space. You know, what can we do next? And it's also to demonstrate that it's made from electronics that are accessible to sort of everyone. You can order these things on the internet and create some custom electronics and put it all together into a really tiny form factor. And so to describe what the form factor is, this new form factor, take us back to 2009. Professor Bob Twiggs, he was actually the co-creator of the Cubesat standard. He saw that Cubesats were becoming more and more complicated. So when you're developing a satellite, there's all these different subsystems, and depending on what your mission goal is, you might have a specific science instrument that you need to develop. And the timelines for developing these CubeSats was getting longer and longer. At the same time, the cost of launching things into space, it's sort of based on a cost per kilo. And the cost of getting these things into space was increasing. So to try and combat these things, he came up with this idea of a pocket cube, a satellite that fits in your pocket. And because it's smaller, it's going to cost less to get into space. It weighs less. And also because it's smaller, it adds a few more constraints on the design of what you can put in there. And so it makes it a bit simpler. And that meant that undergraduate, university students could start building a satellite, in the early years at university and actually have it finished and potentially in orbit by the time they finish their uni degree. Whereas some CubeSat missions were lasting sort of, 5-6 years and people would never get to see it in orbit. So pocket cubes do have some space heritage. They have been launched into space before. The first set of pocket cubes was in November 2013. They were actually on board an Italian satellite. So you've got to get a satellite into space, you need a deployer. So a deployer is a bit like a jack-in-the-box, pushing a satellite out into space. So this Italian satellite called Unisat 5 had a couple of these deployers on board. And inside them were 4 of the first pocket cubes. And they were launched on top of a Russian Nepa rocket, which is actually a converted intercontinental ballistic missile. So Russia have sort of added the guidance to be able to put payloads into orbit for commercial paying customers. But these rockets actually get launched out of a silo underground, and they literally pop up out of the ground, the engines light, and then they take off into space. It's quite amazing to watch. And so these are the 4 pocket cubes that were launched at that time. So T-Logo cube is a 3P. When I say P, it's the units of a pocket cube. So 1P is a single unit, which is 5 by 5 by 5. 2P is 10 by 5 by 5, and the 3P is 15 by 5 by 5. And so that was a team of students from Sonoma State University and Moorhead University in America, and they were, trying to validate the technology, but also testing operating systems and different techniques of controlling satellites in space. The little satellite there, Ren, is a 1P, so that was actually by a German fellow by the name of Paul Kazilla. And his satellite contained a camera and even pulse plasma thrusters, so it actually even had some kind of propulsion in space. CubeSat S1 was designed by the University of Maryland in Baltimore. They actually tested an instrument that they could use on CubeSats and larger satellites. So they use it as a bit of a test bed for technology. And finally is my favourite $50 sat. So like the name suggests, they were aiming to make it for the cost of $50. I mean, you've never heard of a satellite that cost $50 before. But in the end, it actually did cost more than $50. It was about $250, but I'll give them that. But it was proof that something so cheap can operate, and it actually operated for 18 months in space. So for 18 months it was orbiting the Earth, operating, transmitting telemetry, and just sort of saying hello to everybody, and I'm healthy. So I thought that was a pretty amazing achievement. So I've probably only got a few dot points up there about why. Sort of a lot of things feed into why you decide to build a satellite. You don't really sort of wake up in the morning and go, I'm going to build a satellite. I think the first step was actually becoming a space nerd. I'm a self-confessed space nerd. I'm happily admit that. I started getting into space and the technology and the engineering, and it sort of inspires people. It's amazing. You see your rockets launching into space and rovers landing on Mars, and I thought that was just, that's fantastic. And I thought, I could learn more about this. So at the same time, I was becoming interested in electronics. And I discovered that there was this new craze called drones and quadcopters. And I thought, well, I can build one of them. They're starting to be pretty affordable. And so I assembled myself a drone, and I guess it's all well and good, but I guess everyone was building a drone. So I started looking at the software behind them, because it was software that was made public. You could see the code that goes into operating these things, and I wanted to learn more about them. And at the same time, these first pocket cubes had launched. And $50 sat, I talk about $50 sat a lot because it was the one where it transmitted telemetry that could be received pretty easily. And when I say easily, I had those little USB TV tuner dongles that you can plug into your computer and get digital TV from. Well, it turns out they're really good radio receivers. And so if you plug one of them into a semi-decent antenna, you can actually listen to satellites from space. And I thought, fantastic, that's great. So there I am, sitting in my lounge room with my laptop, sitting on my lap, thing plugged into my computer, and I'm waving an antenna across the sky as the satellite passes. And it sounds horrendous. It sounds a bit like a fax, making blah, 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 blah. It's kind of noise. My wife didn't appreciate it, but I thought it was really exciting. And so learning about all these things, and you could create custom electronics really cheaply. And the kind of thing that, years ago you couldn't do cheaply. It was just something that was just beyond the reach of most individuals. It was sort of only a thing that you did as a uni project because they had the funds to be able to do it. And I thought, how can I combine all these interests of mine that, seem to be in different areas? And the answer I found was building a pocket cube satellite. So what's inside OzCube 1? So I said it's got a camera, so it's actually got a 2 megapixel camera. A lot of small satellites from universities have had small VGA, so that's only 0.3 megapixel cameras, but I'm pretty good at Googling things, and I found that you can buy these really small camera modules fairly cheaply. And it's a 2 megapixel sensor. I thought, well, that's okay, but it can talk to these little microcontrollers really easily. So I thought, well, okay, there's a tick there. And just to put into comparison, what can a 2 megapixel camera do from space? Well, it can image everything from Ballarat to Healesville if it's about a 600 kilometre altitude. So which is actually sort of an area of 150 by about 114 kilometres. If it was even lower, it could zoom in a bit more. It could be like 76 by 57 kilometres. So each pixel is about 47 metres on the ground. So it's not going to compete with Google Earth or images anytime soon, but it's something. It's something, That's why we sell cheaper cars, because not everyone wants the big expensive car. Some people just want something that's affordable. Now, because I've got a camera with a lens, anyone who's got a digital camera knows the lens sticks out the front. And so to try and package that into something really small, something had to give. And in my case, it was create a hole in a circuit board. And so that's the lens of the camera pointing up through the power supply module of the board. And so that made it really efficient in terms of the use of space. I could work all the electronics around it. On the right there is a solar panel. You've got to obviously generate electricity in space to be able to charge the batteries and operate the electronics. And so over a few iterations, I designed, I guess, what you see here. It uses high efficiency cells. Because you've got something that's so small, you're really limited in terms of the power that you can generate from the solar panels. So these are high efficiency cells. They're 28%. So the ones on your roof, I'm from Perth, and a lot of people have solar panels on the roof, and the average efficiency is probably like 18 to 22%. So these ones are a bit better. These are 28%, and these are actually offcuts of larger space grade cells. The actual CDH module, the command and data handling, this is the brains of the satellite. It's actually based on a little microcontroller board that is used by hobbyists worldwide. In fact, you can even buy the board for about $3 or $4 from China, and it can perform the same functions. So that board itself was a bit big, so I had to add a few more things to it that I need to. So that's a little micro SD card holder there, so you can sort of imagine the size of the board there. It has a clock module, so it's important that a satellite keeps time for a number of reasons, and for me taking photos, I need to be able to set a timer to be able to take these photos. It has a little 9-axis IMU, so the same little sensors that's inside all these drones and quadcopters. This thing can sort of sense its orientation in space. And it's got some sort of this watchdog timer. It's just a fancy word for when things operate in space, they can sometimes have issues and sort of get confused. So the watchdog timer helps the satellite reboot. So it turns out even things in space need to reboot to fix a problem. $50 Sat was a satellite that demonstrated that you could buy a little radio module that cost about $10, and it works in space, and you can use it to talk to the satellite, and it can transmit stuff down to the ground. So I use that as sort of an inspiration for mine. So the radio module that I'm using is, I guess, in a similar sort of family. It's actually sort of the next generation chipset from the same manufacturer, but it's actually a lot more powerful. Which means I need to manage my power much more carefully. But it means that people on the ground are going to be able to receive those pictures a lot easier. And so I wanted to make my satellite, accessible to people. So having a more powerful radio was a way of making it easily, more easily received. And the tape measure is not there just to show you how big the satellite is. The tape measure is actually the antenna for the satellite. For the technical people, it's a half-wave dipole that uses the 437 megahertz band. But the benefit of using a tape measure is that it folds up nicely when it's in the deployer, and when it pops out into space, things spring out nice and easily. And that's actually the same sort of thing that was used on the first Australian amateur satellite. It was the Oscar 5, and they used a tape measure for their antenna. So I'm sort of carrying on their tradition there. So I just sort of want to talk about what a DIY satellite is. There's no sort of official definition of what a DIY satellite is. I think that it's something that's got to be affordable. And now, affordable is different for different people. But I'm pretty sure that if the price tag is 5 digits or more, that's sort of not affordable anymore. So all the prototyping that I've done for AusCube1 has been in my home workshop. And look, that's pretty limited. It's an electronics project, so you need some kind of electronics tools. So I've got a soldering iron and a little hot air rework station. Because I'm using surface mount components, normally in a factory it goes through an oven. I don't have that, so I just use a skillet, electric fry pan, to help me do some of my electronics. When I'm building AusCube1 for space, obviously there's a few more extra precautions you need to take, but for prototyping and building, you can do these things in your shed. But you do need skills to be able to build a satellite. It's not quite as easy as just buying electronics kit. But these skills are that can be learnt, and they can be learnt easily. And the material to learn this is, we've got the internet. The internet's sort of a worldwide encyclopedia of things. And so there's nothing like actually getting in and doing things. So I started making these custom circuit boards, and I made mistakes, and some of them look terrible. But as you start practicing and doing things, you become better at them. And so you can get tips from the internet, and now I'm sort of fairly proficient at doing this kind of thing. Another aspect of a DIY satellite is that it might use open source hardware or software. Now, it's not really a prerequisite for a DIY satellite, but open source sort of means that either the information is all available already on the internet and you've got access to that, or you write some code and make that available to other people so that other people can either help improve your project or do another project down the track. Sort of a bit of a sharing society. So there's no proprietary stuff in open source. Everyone's sort of it's open to improve it, and hopefully, at the end of the day, it becomes better and more capable. So I just want to list a few satellites that I call DIY satellites, and sort of where they've started from. As I said before, $50 Sat was probably, I guess, a big influence on my project. They actually published all the information on their project online. And, I don't know, I'm not sure if it had been done before, but, even things like the actual circuit schematics, you could grab their designs and then order the same circuit boards yourself and have the custom circuit boards. You still have to assemble them yourself, but all the information about how you could communicate to it was available online. So that was actually a collaboration between Moorhead State University in America and 3 amateur radio guys from the US and UK. And so the fact that something that's cost $250 to build and works for 18 months is pretty amazing. Another DIY satellite is this Aussie. So it was actually, so it's a Cubesat. The open source satellite initiative was made by a Korean gentleman called Ho-Jun Song. He was not an engineer, he was an artist. And he actually wanted to create this as an art project. And it had really bright LEDs that he hoped that would flash from space and people could see messages from the sky. But he was never able to make contact with the satellite. It never operated correctly in space, so he was never able to achieve a complete mission success. But because the project was open source, he made the information available to others so they can take what he learned and then improve on that, and hopefully they can have a successful project down the track. You might, these are a couple of satellites from JPL, so you go, that's a government organisation, that's not necessarily a DIY satellite, but the PhoneSat series used an Android mobile phone. They actually used the brain, they stripped down a mobile phone and put that inside a satellite chassis. Because the mobile phone's really good. It's really compact. It's got lots of really useful sensors, like it's got a camera. It's got those same gyroscopes that you find in those quadcopters. It's got a lot of processing power. It's even got GPS receivers. So in my mind, it's because it uses Android, it's an open source, kind of open source operating system, and people can modify it and add to it fairly easily and make their code available. So I've sort of put that on my list of DIY satellites. Another DIY satellite is this NanoSat Eye in the Sky, which is actually being designed here in Melbourne by Mark Smith. He's a Melbourne local. He might disagree with me calling it a DIY satellite, but like other satellites, you've got to go through a sort of prototyping phase, and their initial prototype is going to be using some of these controllers that are the same as these drones. So with the drones, you need to be able to communicate to them and get some telemetry back from them. So their initial prototype is going to use that same kind of technology. So eventually they'll plan to use sort of potentially more closed source things, but at this early stage, it's still sort of a DIY satellite. Some DIY satellites are actually built from kits instead of being developed from scratch. So a company called Interorbital Corporation, they sell this Cubesat kit. So it's like a round cylinder. And you can actually buy a launch and satellite kit. But at the moment, they still haven't launched anything to orbit, but you can still build the electronics kit. But this form factor was enough to inspire people to actually write books. So this satellite is Project Calliope. It's the name given to a project by Sandy Antunes. So he actually wrote a series of books about DIY satellites to give tips on what he'd used to build his and do testing at home, because you want to make sure that your satellite works in space. So you've got to subject it to a bit of torture before you actually get it into space. So he talks about things like vibration tests using orbital sanders and homemade vacuum chambers using pressure cookers and things like that. So there's a lot of useful tips that sort of DIYers like myself can use when you're testing your satellite. And some DIY satellites don't even have to go to space. My project actually started by, I wanted to build a satellite. It might go to space, but it was sort of a little robot that doesn't move. That was just something that I wanted to build. Apparently I've inspired a 14-year-old kid in UK. He's actually built his a pocket cube. So I gave him a few sort of tips via email, and he entered that in the 2015 Google Science Fair. So not everything has to go to space. I've probably bitten off more than I can chew by going straight for something going into space before building a kit first, but some people are gluttons for punishment. But one thing that I learnt pretty quickly was that there's not a lot of resources out there about sort of how to build a satellite. And maybe that sort of stems from the fact that things going to space could be used for nefarious purposes. But I managed to learn a lot of what I learned from other Cubesat missions and space missions. So a lot of people write papers and do presentations about what did work and what hasn't worked in their satellites. And I've taken bits of information from all those and put it into building mine. But some people aren't as good at filtering that kind of information. So I thought that you need to have some kind of kit or some kind of first programmable electronics kit. So as a sort of side project, I've made this educational satellite called EduCube. And it's really to teach kids about it's okay to do software encoding, that's fine, but at some point you still need to deal with the hardware, you still need to deal with the electrons to be able to charge batteries and actually power these circuits where you can write this code for. So what I'm building is sort of, like a satellite that's not going in space. I call it the satellite for the classroom. And that's programmable really easily using these open source tools, it's based on an Arduino. So a lot of hobbyists it's the same actual microcontroller that Ozcube uses. But it's just designed to be a bit more accessible, and it's going to teach kids about physics in a fun way with a space focus. So it's got sensors like a barometer, a temperature sensor, humidity sensor, so it can be used as a weather station. It can be used to do a whole bunch of different science experiments, but remembering all the time that it's a satellite, and there is a destination for all these skills that is with a space focus instead of industrial control or something like that. And look, that's where I am at. That's what Ozcube is. Is there anyone with any questions at all? Yes?
What do you mainly use them for?
I'm sorry?
What do you mainly use them for? The photos.
Oh, the photos. Well, the photos are just to show people. People can relate to photos. I think you look at sort of the modern generation, we use social media a lot. And it's only nerds that like beeping from space. Not everyone gets excited about that, but everyone can relate to a photo. They can sort of look at that and say, oh, look what's happening there, or look what happened, there's my house down there. So that's something that can sort of, bridge that gap to people to say, look, this is something that's happening in space, but you know what photos are like, you take them all the time on your phone. So it was just a way to sort of make it accessible to people.
You mentioned you're launching your Ozcube 1 into space. What are you doing about the actual launch?
Okay, so the question was, how am I getting Ozcube 1 into space? So, I guess a lot of testing needs to be done before you actually get something ready for space. So, because this is a solo project, so I don't have a whole team of people working on it behind the scenes. So if I'm not working on it, then no one's working on it. So I've sort of taken the approach that when the satellite's finished, I've gone through the whole sort of testing to be able to make it ready for space. But obviously getting things into space is expensive. Even with something this small, it still costs a fair chunk of money. And so we're talking about $30,000 for something like this to get into space. So I've got a GoFundMe campaign to raise the funds for the launch and to do proper testing. So it's okay to do testing at home, but really when you're sending things on someone else's $1 million rocket, they want a bit of assurance that you're not going to break their thing. And so in Canberra, there's a big testing facility there. So I'm hoping to basically raise the funds to be able to do a proper suite of testing, and once that's done, I guess get the funds to actually send into space. So the only taxi ride at the moment is on top of a new Italian satellite, so the Unisat 7. So the one that launched the first Pocket Cubes was Unisat 5. Unisat 7 has the Pocket Cube deployers on it, and obviously if I raise the funds, I'll be able to put it on board that, and that'll go on top of the Russian rocket again and off into space. But I'm not too worried if I miss that taxi ride, because there's a lot of companies worldwide that are developing lower cost launch vehicles for CubeSats, and I can see that there's going to be a lot more rides in the future. So if I miss this train, I'm sure there'll be plenty more.
And what's your GoFundMe page?
GoFundMe.com/Ozcube1. If you come to my stall, I've got a little brochure with the links, but Ozcube1 is on social media, on Facebook and Twitter, so you can always follow the project there if you want to.
What causes these satellites to stop functioning? Is it like the gravity or like radiation? Or?
Yes, radiation. The low Earth orbit environment is actually it's not too bad. We're in where the space station is. So the space station is about 450 kilometres. So around that height, you're still protected by the magnetosphere of the Earth. So you can use off-the-shelf electronics to do that, but there are times when you get cosmic rays and they can sort of turn things on that aren't supposed to be turned on the satellite, and that can mess up your code. So you need to take precautions to be able to cope with that. So, and that's why you have the watchdog. That sort of helps the satellite reboot and sort of clear that error. And so some of that's hardware, some of that's software. So there's different tricks that you can do to take that into account. Hi.
So I'm sure there must be some legal obligations in terms of launching internationally or nationally.
Yeah, so there's anything that gets launched, that's an Australian object that gets launched overseas requires a permit from the government. So you need to get an overseas launch certificate. So that's, I guess, one of the regulations that sort of you need to get a license for. Because I'm operating this as a not-for-profit, it's using the amateur radio bands, I guess I need to be a licensed radio amateur, but there's still a frequency coordination process and sort of a license to be able to operate the radio as well. So you need to get them before you then buy your ticket into space. Okay?
Any more questions? No? Oh.
Yes, actually, I've just been sitting with this niggling thing in the back of my mind in terms of where we stand internationally in terms of security at the moment, and how. I just had the question about background checks on people actually being able to launch.
I couldn't tell you that. The Department of Industry that do these overseas launch certificates may have that criteria. I'm operating, because the legislation has undergone their recent review, so they may be sort of changing how they do things. I'm not aware of the behind-the-scenes process, but I'm attempting to operate mine as the current legislation basically says you're either commercial or you're scientific or educational. There's no grey area, that's sort of what they define. So I'm hoping that my mission is going to be classed as a scientific or educational program, and you obviously got to, you basically got to give them all the dirty about the ins and outs of what's inside your satellite and what it's going to do. And they take all that into account. There's a whole lot of risk management that they need to do, and you need to sort of prove that your satellite's not going to cause damage to anything else. And they probably do background checks on you, but I'm just not privy to the ins and outs of what the government departments do.
So have you taken it? Oh, sorry. Have you taken it to other scientists, like atmospheric scientists, pollution management scientists, or something like that? The photographs, or something that you could look at collaborative research, so for funding, or?
Not yet. It's people are a bit sceptical of guys building satellites in their garages, so they tend to want to see it sort of work first, and my sort of approach is, I want to build this for me first. It's going to be a platform that's built fairly cheaply, and it's AusCube 1 for a reason, because that's the first one. Hopefully there'll be many more afterwards, and then I can say, well, this is a proven platform that didn't cost too much. It's going to be a lower risk for then you to do your research and that kind of thing in the future. So there's always room for future missions. But yes. Maybe not for the first one, but definitely going forward.
Do you think Australia as a country sort of has a future in the satellite industry, not just for amateur?
I think we're a bit behind the 8 ball when it comes to things like that. So Australia needs to find a niche that other people aren't doing yet. You don't sort of create a new car company from scratch when you don't know anything about creating a car company. You start from sort of some kind of existing base. Probably a bad example because we've got rid of the companies that make cars here. But Australia is very strong in a lot of scientific fields. We're very strong in astronomy and things like that. So we've sort of got a niche there where people sort of, I guess there's a lot of talent in that area. So the satellite is, sort of what I'm building is just a tool. It's like a spanner, What are you going to do with that tool? So the payload of these satellites. Building the vehicles is okay, but it's deciding on what do you do with it. What kind of missions do you do? So I definitely think there's plenty of people in Australia that are building satellites. University of Melbourne, University of New South Wales, South Australia, they are building these satellites for scientific research. So that's the vehicle. What can we put on that vehicle? So I definitely think that we've got an opportunity there to sort of cement our place in the worldwide scientific community for that kind of research. Commercially, I guess it's yet to be seen. Other Australians have gone overseas. Planet Labs was actually founded by an Australian, but he didn't see Australia as a place where he could really sort of follow his business model, and so they went to America. I like Australia. I like to stay here, and so I'm obviously trying to push some kind of industry here. Finding out exactly what to do, well, I guess that's yet to be seen.
Are these satellites capable of going beyond Earth's orbit?
Anything's capable of going there. Actually operating out there is a different story. So when you're talking out of low Earth orbit, sort of into sort of deep space or geosynchronous, you have a lot more radiation out there, and so generally radiation tolerant or hardened parts are much more expensive. As in, at least 1,000 times more expensive. And so it's difficult to sort of make a low-cost thing that can survive that environment, unless you're using a lot of sort of, novel techniques to manage that. It's not to say that it can't be done, but generally it does cost a bit more. So even the little microcontroller that I'm using in mine, the manufacturer actually does make a radiation-tolerant version. So it's not hardened. It means it can only tolerate a higher dose of radiation. So there is a potential there for using this kind of satellite in a deep space or a moon-type mission or even Mars. You need to build your system with that in mind. So you need shielding and you need better solar panels. So generally it is going to cost more, but it can be done. But it's just it's all about money. Yes.
Once it's in space, do you have any control of where it goes?
So AusCube1 uses passive pointing, so passive magnetic stabilisation, which is just a fancy way of saying that it's got a magnet on board. And so that helps the satellite orientate the camera lens down over Australia, and when it goes over the northern hemisphere, it'll point up. But it's determined by when the rocket releases me into orbit, that's pretty much the orbit that it's going to stay into. So it doesn't have propulsion, and it doesn't have any active way of pointing any particular way. One of the techniques that I'm going to be using is the same as was used by $50 I don't know if you saw in the slide that the antenna, the tape measures were actually covered by a sort of a yellow gold sort of foil. And what that does is just increase the surface area of those antennas. And even though it's in the vacuum of space, there still are particles and gases out there, and that provides a bit of friction, and it slows your satellite down. And so that slowdown will actually cause it to deorbit much faster. And so using that technique, it will probably deorbit in about 4 or 5 years. There's sort of a standard for Cubesats that they should deorbit within 25 years. And so you've got to show the calculations. That's one of the requirements for getting into space, is that you need to show that it's going to be able to deorbit within that period and not cause damage to anyone else. So I'm hoping that mine will deorbit within about 5 years. But no, I can't guide it anywhere. It doesn't have propulsion. Maybe a future satellite does have some kind of ability, but just not this one.
Any more questions?
If you've got any more questions, anyway, I've got a stall over at a booth over at the exhibit hall. So if you're interested in space, come and have a look at the other booths at the exhibit hall. I'm sure there's plenty of people there happy to show you their wares and talk about what they're doing in the space industry.
Awesome. Well, thank you so much for your time this morning.
No worries.
And lots of awesome questions there, so thank you to the audience for that. And thank you very much.
Thank you.